How to Create the Universe, The God Series Book 32, by Mike Hockney. This free audiobook series has been brought to you by the Foundation of Illuministic Guides. Contact the Foundation publicly as The Phoenix at tinyurl.com/foundation322. Check our foundation page at tinyurl.com/foundation323, and we have a posting group with many books and resources at tinyurl.com/foundation324. For the complete books that will be covered in this series, see tinyurl.com/hockney322. Remember, there are many truths within lies and lies within fact. Truth is relative to the observer. The sign of a seeker is the quest for the truth. In that sign you shall conquer. Find the path in your own quest for the Gnostic Grail of illumination. Choose wisely. We will be watching you. In a Hox Signovinces, Chapter 8, Splitting Light. No experiment would be more earth-shattering than the one that showed that a photon can be split into a chronon and quoron. An entirely new theory of matter can be constructed from these particles. In a photon, a chronon of a certain frequency is perfectly allied to a quoron of the same frequency. They have an analytic, orthogonal relationship, hence they create a dimensionless union. They are the agents of mind. Now imagine taking a vast set of photons and subjecting them to the incredibly high energy of the Big Bang. This succeeds in splitting many of the low energy photons into their component chronons and quorons. Once this is done, we can then start putting them together again. But what if we join them together non-orthogonally? And what if we put together chronons and quorons of different frequencies? It's when these mismatches take place that we generate new types of particles, material particles that exist in space and time rather than dimensionlessly. To be clear, when chronons and quorons are perfectly matched up, we get photons, which are particles that exist in an immaterial frequency domain of mind, a singularity. When chronons and quorons are put together in any way other than perfectly, we get all of the particles of the material world of space-time. Every material particle, like every photon, is a combination of a time particle and a space particle. In the case of photons, the time and space particles are so mathematically well balanced that photons are both dimensionless and immaterial. In the case of material particles, this is not the case. Material particles, despite comprising mismatched time and space particles, can nevertheless produce highly stable particles such as electrons and quarks. In turn, quarks can come together to produce stable protons and neutrons. That is, there are mathematically stable ways of combining non-matched quorons and chronons. Perhaps a wave with exactly twice the frequency of the other wave will work, or a wave with a phase difference of 30, 45 or 60 degrees compared to the other. The idea is to build up a set of stable sinusoidal patterns that we can then map to all of the known material particles, and show that they are actually derived from photons. That is for mathematical sinusoids. This turns them into mathematical rather than scientific entities. In this way, we can reduce the entire particle zoo to an analytic sinusoids, and replace science with ontological mathematics. The uncertainty principle. The position and momentum of a particle cannot be simultaneously measured with arbitrarily high precision. There is a minimum for the product of the uncertainties of these two measurements. There is likewise a minimum for the product of the uncertainties of the energy and time. This is not a statement about the inaccuracy of measurement instruments, nor a reflection on the quality of experimental methods. It arises from the wave properties inherent in the quantum mechanical description of nature. Even with perfect instruments and technique, the uncertainty is inherent in the nature of things. http://hyperphysics.fiastra.xu.edu/base/answer.html. It is stated as a fact that uncertainty is inherent in the nature of things. This is not a fact. This is an interpretation given the ideology of materialism and empiricism. This uncertainty vanishes as soon as we move to ontological mathematics, predicated on the principle of sufficient reason, which guarantees certainty and precision. It's incredible how often science assumes that its dogmas are factual rather than mere beliefs, opinions and interpretations. No one has ever seen a random event, a probabilistic event, an indeterministic event, an indeterminate event, an event without a cause. People see events, and then interpret them in various ways. Even if the event can charitably be called a fact, The interpretation of the event most certainly cannot. That's a reflection of someone's unproven belief system and ideology. Science itself is an unproven, and unprovable, belief system and ideology. As we have shown, Planck's constant corresponds to the smallest possible particle, the flowing point. It is impossible for anything to have a smaller size than this. This is the actual reason why you can't specify the position of any particle more precisely than this. The only thing smaller than a flowing point is a static point, which is a non-existent. Consider these remarks by John Baez. There's an energy operator in quantum mechanics, usually called the Hamiltonian and written h. But the problem is, there's no time operator in quantum mechanics. This makes people argue a lot about the time-energy uncertainty relation, whether it exists, what it would mean if it did exist, and so on. Matthew Donald wrote something interesting about this subject. I'm editing it a little bit here. Most treatments of the time-energy uncertainty principle point out that you do have to be careful to consider the meaning of T. T isn't an operator in quantum mechanics. Uncertainty relations are mathematical theorems as well as physical statements, so if we begin with a proof we should end up with an exact definition of what we are trying to understand. There are probably several forms in which the time-energy uncertainty relation can be proved. From your uncertainty relation we then have T, H, /2 the famous time-energy uncertainty relation that everyone keeps yearning for. The problem is, for physically realistic Hamiltonians H1 can prove there is no operator T with H, T, equals E. In other words, there is no time observable. Time is a disaster for science. Science has no idea what time is. It doesn't know if it's tensed or tenseless, dimensionless or dimensional, absolute or relative, real or unreal. Is it a forward arrow? Why not a reverse arrow? Is it psychological? Is it connected to subjective consciousness? What is time in relation to the unreal, abstract, deterministic wave function? What is time as regards the arbitrary, observer-triggered, indeterministic collapse of the wave function? Science refers to time in all sorts of contradictory ways, and no one really seems to notice or care. No scientist ever seeks to put time on a proper ontological and epistemological basis. It is always used as a heuristic. People choose whatever version of time suits their present purpose, and ignore all of the other versions that don't. Wikipedia says, in quantum mechanics, the position operator is the operator that corresponds to the position observable of a particle. The eigenvalue of the operator is the position vector of the particle. Masahiko Yamaguchi wrote, in quantum mechanics, position is an observable, but time may not be. I think that time is simply a classical parameter associated with the act of measurement, but is there an observable of time? And if the observable will exist, what is an operator of time? Daniel wrote, time is not a variable in quantum mechanics, QM, it's a parameter, much in the same way as it is in classical, Newtonian, mechanics. Mistake Inc. wrote, in the first chapter of Srednicki's book on QFT he states that one route to QFT is to promote time to an operator on an equal footing with position. He says this is viable but complicated, so in general we do QFT by demoting position to a label on an equal footing with time. I don't know more about this but hope it may be of interest. Arnold Neumayer wrote, the problem of extending Hamiltonian mechanics to include a time operator, and to interpret a time-energy uncertainty relation, first posited, without clear formal discussion, in the early days of quantum mechanics, has a large associated literature. Time measurements do not need a time operator, but are captured well by a positive operator valued measure, POV, for the time observable modeling properties of the measuring clock. Drake wrote, in QM, the temporal variable t is not an observable in the technical sense, that is, in the same sense that position and momentum are. In order to be an observable, it should have to exist a linear self-adjoint operator t whose eigenvalues t were the outcomes of measurements. A. de Saint-Hours wrote, time plays a problematic role in the framework of the canonical approaches to quantum gravity. This should not come as a surprise once one accepts the initial incompatibility between time in QM and quantum field theory, QMT, on one hand, and time in general relativity on the other. Indeed, time in QM is substantival in nature. The parameter t that is involved in Schrödinger's equation is an absolute external parameter. It is not described by an operator. This would be in contradiction with the boundedness of the energy, as noted by Alfredo Masses and Hernando Quevedo. It is not a fundamental element of the scheme, but it must be introduced from outside as an absolute parameter which coincides with the Newtonian time. Since there is no operator which could be associated with time, it is not an observable. Consequently, time is not a dynamic variable in QM. In QFT, the picture is similar, since absolute time is replaced by a set of times, the times of special relativity, that refer to Minkowski spacetime. Since this spacetime constitutes a background, it is substantival in nature and the time variable is a background parameter. Instead of absolute Newtonian time, we now have a different parameter associated to each member of the distinguished class of inertial frames. The two absolute concepts of Newtonian physics, that is space and time, are now replaced by the single concept of space-time. Nevertheless, in special relativity space-time retains much of the Newtonian scheme. Although it is possible to find an absolute difference between space and time, space-time is still an element of the quantum theory which does not interact with the field under consideration. That is to say, space-time remains as a background entity on which one describes the classical, relativistic, and quantum behavior of the field. Mrs. Incovido. Space-time in QFT is an external non-dynamical entity like the absolute time of QM. In GR, there is a drastic difference with QM and QFT, since here time is dynamical, local and does not constitute a fixed background. In GR, space-time is dynamical and therefore there is no absolute time. Space-time influences material clocks in order to allow them to show proper time. The clocks, in turn, react on the metric and change the geometry. In this sense, the metric itself is a clock. GFA, time in GR is not an external parameter. GR does not possess a naturally preferred time variable whereas QM and QFT do possess such a preferred time. What a mess! How can science proceed without proper, agreed definitions? Scientists make up the meaning of time as they go along. They use whatever interpretation suits their pet theory of the time. They use different paradigms to discuss time, all of which are incompatible. These problems can all be swept away by the simplest adjustment. All that science needs to do is replace time with 3D imaginary space, and treat it in exactly the same way as 3D space, but orthogonal to it in a complex domain. However, this involves switching from scientific empiricism involving real numbers to mathematical rationalism involving complex numbers. Believers in the religion of scientism refuse to take this rational step. As soon as we recast time as imaginary space, completely analogous to real space, we can rewrite the uncertainty relations as QR, PR/2, where R signifies real space, and G, pi, I/2, where I signifies imaginary space, time. We can also write T, I/2 where T relates to imaginary space, and I is imaginary energy, and S, E/2 where S relates to real space. You can no more say that energy can be borrowed from time, imaginary space, than you can say that energy can be borrowed from real space. At a stroke, all sorts of absurd scientific speculations about borrowing energy from time to achieve certain goals, and then rapidly repaying it to balance the books, are expressly forbidden. Given these considerations, the equations of quantum mechanics have to be altered to treat time on a par with space, rather than as an external parameter. The Bloch universe. So, you think you know about time? Try to answer this question. Is the Bloch universe notion compatible with general relativity? It certainly seems consistent with special relativity, but isn't time explicitly adjustable in general relativity? Indeed, isn't the same true for space? Robfi wrote, the modern view, used by working relativists, is that general relativity works with a space-time consisting of an arbitrary four-manifold M with a Lorentzian metric tensor field Gab, whereas special relativity is the special case where the space-time is the Minkowski space-time consisting of R4 and their flat Minkowski metric Gab. Roberto Mangabuanga and Lise Milling wrote, general relativity must be reformulated without the addition of the Riemannian space-time conception, the disposition to spatialize time, or the Bloch universe view, none of which have indicated by the empirical and experimental evidence adduced in favor of general relativity. The metaphysical gloss must be lifted from the empirical theory. So, Why do so many scientists associate the block universe with general and special relativity? It's not at all clear that space-time in special relativity has any connection at all with space-time in general relativity. Remember, there are no forces present in special relativity, which makes it rather hard to see why it should be connected to the four-space theory of general relativity. It's rather like trying to understand Fourier material space-time functions exclusively from Fourier material frequency functions outside space-time, without ever mentioning space-time and matter. In ontological Fourier mathematics, the addition of space, time and matter changes everything. Similarly, in relativity, the addition of force changes everything. Special relativity is actually a theory of light, with matter being compared to light in non-force situations. General relativity is a theory of matter, subject to forces. Unification. Among the different attempts to unify GR and QM, one can distinguish the canonical approaches that make use of the Hamiltonian formalism, in which space-time is foliated and an appropriate canonical variable is chosen. This program is a direct quantization of Hamiltonian GR. In the spirit of GR, it does not assume a background space-time. According to the choice of the variable, one can specify different subclasses of quantization. 1. The oldest version is quantum geometrodynamics, in which the canonical variable is the three-dimensional metric. 2. Since the end of the 1980s, this approach is pursued in a different form based on ideas of a Bay-Ashker in which the canonical variable is a three-connection. This has led to loop quantum gravity, LQG, covariant approaches. This line of research has led to string theory and M-theory, some over history's line of research. Others, such as twistor theory, non-commutative geometry, causal sets. -A. To St. Towers. Science can never succeed until it relies on rational and logical principles and agreed ontological and epistemological definitions of space, time, energy, mass, matter, speed, and so on. There's absolutely no chance of that while science remains wedded to empiricism, materialism and heuristics.